Okay, so yeah, so regs. So regs are right-angled Artin groups. In case you don't know what they are, the idea is you take a simplicial graph. So simplicial just means that, well, you've got some vertices, and you've got some edges, and there aren't any multiple edges, and there aren't any loops. So in other words, it's a simplicial complex, which is one-dimensional. And then associated to any simplicial graph, there's a group called a rag, right-angled Artin group, and it's generated by the vertices. So the graph that I've drawn has six vertices, and the relations are that things commute if they're joined by an edge. So in fact, A and B in this picture commute because they're joined by an edge. B and C commute, C and D commute, D and F commute, D and E commute. And so that gives you a presentation for a group, and that any such group is called a rag. So there are two extreme cases when you just have some vertices, and so you get generators and no relations, so that's a free group. And when you have a complete graph, you got some vertices, and all the generators commute, and that gives you a free abelian group. And in between, there are lots and lots of very interesting groups. Right, so I'm looking at the group of outer automorphisms of these rags. So that's outer automorphisms modulo inner automorphisms. And I'm interested in finite subgroups of this group. So there's some obvious finite subgroups. All you need for a finite subgroup is you need something, right. All you need to get an automorphism is you need some map on the generators that preserves the relations. So if you invert one of the generators, it doesn't change anything about what commutes and what doesn't. So that gives you an automorphism. So you get a little copy of Z2 to the number of vertices. That's a finite subgroup of out of A gamma. Another thing that you can do is if you take your graph and you perform an automorphism of the graph, well, edges go to edges, non-edges go to non-edges. So it also preserves the commuting relations. So that also, any graph automorphism gives you an automorphism of the group A gamma, and there's only a finite number of graph automorphisms, so you get a finite subgroup of out of A gamma. The group generated by inversions and graph automorphisms, oh yeah, I was going to figure out, I always forget which one's normal, and I was going to figure that out before I started talking, but I forgot. Does anybody know which one's normal? And I got it right, good. Yeah, right. Okay, and so that gives you a bigger set of subgroup, finite subgroup, which sometimes we call the Weil group associated to A gamma. And of course, if you have a finite subgroup and you take a conjugate of the finite subgroup, you get another finite subgroup. So there are some obvious finite subgroups in this outer automorphism group. I wonder why this is. But it turns out that there's also lots and lots of very interesting other finite subgroups. I've just drawn an example of one where gamma is a discrete group. There's an automorphism. It's not just a permutation of the generators, and it has order 4. That's just one simple example. Exercise, come up with examples. So the question I want to address today is how many finite subgroups are there in out of A gamma? In particular, are there only finitely many? Of course, there's infinitely many because we can take conjugates, but up to conjugacy, are there only finitely many finite subgroups of out of A gamma? So if gamma is a complete graph, and we're looking at z to the n, automorphisms of z to the n is just the general linear group GLNZ, and there the answer is very classical. So if you got z to the n, in the 1880s, Minkowski noticed that if you go mod 3, then the kernel of that map is torsion-free. So if you have a finite subgroup of GLNZ, it injects into GLNZ mod 3z. So therefore, there's only a finite, that's a finite group. So finite subgroups are isomorphic to subgroups of GLNZ3. So that means there's only finitely many isomorphism classes of finite subgroups in GLNZ. And then Zassenhaus in 1938 used work of Jordan from 1890 to prove that there are only finitely many conjugacy classes of subgroups isomorphic to a given finite subgroup G. So corollary conclusion, there's only finitely many conjugacy classes of finite subgroups in GLNZ. So that's classical even by my standards. 1938 was a while ago. 1938, right. Okay, so what we want to do is talk about general gammas, not just z to the n. And what I want to do, I want to describe all finite subgroups up to conjugacy. And I would like to do this geometrically, or at least combinatorially. And so for that, I need to think about these groups and these subgroups in terms of spaces, complexes. So whenever you have a right-angled Artin group A gamma, there's a complex called the Salvetti complex associated. So it's got 1 0 cell. It's got a loop for every generator. And it's got a torus for every edge. So if A and C are commute, then I have to glue on a little torus onto that. And if A, B, and C commute, I have to glue a whole cube onto that, and like etc. Yeah, I can't do this. A, B, and B is supposed to be parallel to that B, etc. Okay, so in other words, if all those three guys commuted, I would get a three-dimensional torus. If two of them only commuted, I would get a two torus with a loop stuck around it. And so this is called the Salvetti complex. And it's got some basic features. First of all you have to do is look at the loops and the squares. And what you get is a presentation complex for the group. You get a space with whose fundamental group is A gamma. What gluing the higher dimensional cubes gets for you is that all of a sudden the space that you make has a universal cover which is cat 0. So in particular, it's contractible. So now you have the fundamental group, namely A gamma, acting on a contractible space with compact quotient. And as Andy explained this morning, you can say another way to think of that is that S gamma is K A gamma 1. So in particular, its homology is the same as the homology of S gamma. But today I'm not talking about homology, but it's still a good fact. Right. And we had this finite subgroup that sits inside of any out of A gamma, generated by inversions and graph automorphisms. But you can realize any such thing as an isometry of this space, S gamma. If you got an inversion, you just take that loop and turn it around, and that induces a map on the whole thing. A graph automorphism kind of mutes the picture. It still gives you an isometry of the thing. So whenever you have So anyway, you get an injection of this whole group sitting inside of the isometries of S gamma. Whenever you have an isometry of S gamma, that induces a map on the fundamental group. And that gives you the element of W gamma that we're talking about. So anyway, the image of, so this group, W gamma can be realized as isometries of this complex. Right. And in fact, so if you have an arbitrary marking of this S gamma, so by a marking I just mean a homotopy equivalence. Then, and you have any isometry, then you look at what this does on pi 1, and it gives you an element phi bar in an automorphism of A gamma. And what it does is conjugate your subgroup W gamma to something, to the conjugate by the induced map H star. So you can get all of the subgroups I've mentioned so far, you can get from this picture of isometries of this space plus markings. Right. And in fact, whenever you have any space with a marking, any space whose fundamental group is A gamma, I should have said that. And you've got a marking, then you get a map from the isometries of X into out of A gamma. And if you have a finite subgroup, H, then you get rho of H sitting inside here is a finite subgroup of out of A gamma. Okay? X is any space whose fundamental group is A gamma. Sorry? Yeah, okay. Let's make it a metric space just so that makes sense, so that my slides are right. But you don't need, we could talk about homeomorphisms of X. S gamma is so H is just a homotopy equivalence from X to my K gamma 1. No. No, it just has the same, it's a homotopy equivalence. Yeah, I guess so. Yeah. Okay.
And maybe X is like, maybe you require K gamma 1 to be CW half
Okay. Yeah, but yes. For all intents and purposes. Okay, whenever you have a space that's nice enough and has, actually all you need is the same fundamental group. You don't even need it to be a homotopy equivalence. As long as it's got but let's, the spaces I'm going to be talking about are actually going to be K gamma 1s, so yes. Okay, so, right. And the reason I said that is I want to introduce this terminology. I want to say that the group G, a finite group, CH actually, G, is realized on X. So what I mean to say that a finite group is realized on a nice space X is that there's a homotopy equivalent from X to my standard S gamma that so that rho of H is my group. That's what I mean to say that G is realized. I can see G as it'll be isometries of a nice space. That's just to introduce the terminology. Okay, I'm trying to prove that there's only a finite number of conjugacy classes of finite subgroups. So the idea is I want to find a finite collection of nice spaces, X. Each of them has to have a finite isometry group, and every finite subgroup can be realized on one of my spaces. That's the plan. Is that clear? Okay, good. Okay, so let's look at, so I already discussed this problem, not in this way, but for the z to the n, but let's look at the other extreme. When my graph is discrete, then A gamma is a free group, and if I've got a finite subgroup of outer automorphisms of the free group, there's a theorem due to Color, Grantzoff, and Zimmerman separately in different languages. Color proved it in English, Grantzoff in Russian, and Zimmerman in German at about the same time. They proved that you could realize that you could always find a finite graph. In fact, a graph with no separating edges, which realizes your finite subgroup. Now, there's only finitely many graphs with no separating edges and a given fundamental group. So that implies that there's only finitely many conjugacy classes of finite subgroups of out of Fn. So the fact is that I want to prove is true for out of Fn. And actually, the fact that you can realize subgroups by thinking of them as automorphisms of graphs is useful in lots of other ways. You can prove classification theorems about finite subgroups. For instance, you can figure out what all the finite p subgroups are in out of Fn. You can figure out the maximum order of a finite subgroup by using the fact that any finite subgroup can be realized on a graph. And a bonus is that if you look at the abelianization map from the free group to z to the n, that induces a map on automorphism groups, and in fact on outer automorphism groups. And Edna Grossman proved that the kernel is actually torsion-free. So what does this mean? If you know something about finite subgroups if you find interesting classes of finite subgroups in out of Fn, you'll get interesting finite subgroups in GLNZ. So even if you're only interested in GLNZ, it's interesting to look at out of Fn and graphs. Yeah, I guess so. Yeah, okay. This is another proof. That's the proof I want to, yeah, that's the proof I want to look at.
But no, the kernel torsion-free, that probably uses this.
Yeah. Yeah. I'm not sure how she proved it. She proved it before these guys proved their theorem. Yeah. So I'm not sure how she proved it.
And this way of Artin, can it be the way that makes C out of N profinite?
Is profinite.
Yes. Maybe the limit of finitude.
I doubt that that's true.
That would mean it's uncountable.
That would mean what?
That would mean it's uncountable because inverse limit of finitude.
Yeah. Okay, good. Okay, so now I want to go to general graphs, gamma. And I want to think about outer automorphisms of A gamma. So this group depends seriously on the structure of gamma. Out of Fn is definitely not the same thing as GLNZ, so you can already see that there. But I want to outline, yeah, so what do we need to think about when we're thinking about the structure of out of F gamma? How do we get automorphisms of A gamma? Well, here's some terminology. If I start with a vertex X, then the link of X is going to be the subgraph spanned by all of the adjacent vertices. So if that's my X, then these guys are adjacent. And that's the link, the red stuff. And then the star of X is going to be the graph spanned by the link of X and X itself. So the blue subgraph plus the red subgraph, that's the star of X. Maybe I'll do that. So the blue thing is the star of X. And if you look at the rest of the graph, after you get rid of the complement of the star of X, you get, it breaks into components. There's one component, here's another component, here's another component, here's another component. So some of these components are some of them are singletons, and some of them have more than one vertex. So we'll call the ones with one vertex Y and call the ones with more than one vertex C's. Okay, so this picture is important for understanding automorphisms. Right, so I claim that these are some basic Whitehead automorphisms, which we're going to call Whitehead automorphisms. In this picture, if Y is a singleton, you can take Y and multiply it on the left or the right by X or X inverse. Why can you do that? Well, everything that commutes with Y also commutes with X. So if I multiply X by Y, I won't destroy any commuting relations. I'll preserve commuting relations. If I try to do that with something that's in one of these connected components, well, if I try to multiply X by Z, then it's not going to commute with that other guy, Z prime and C, right? Anymore. X doesn't commute with Z prime, so XZ isn't going to commute with Z prime. So I can't do these. What I can do, however, is conjugate everything in that component by X, and then things that used to commute still commute. Okay? So these two kinds are called right and left folds for reasons, well, having to do with graphs. And this is called a partial conjugation, because I'm only partially conjugating one piece of the graph by X. And those are the three types of basic Whitehead automorphisms. So I want to make a definition. I want to say, I want to define a subgroup of out of A gamma. I want to be to the subgroup generated by Whitehead automorphisms plus inversions. If I do that in the case where I've got a free group, then actually I get the whole group out of A gamma. On the other hand, if I go to the other extreme and look at Z to the n, well, there aren't any Whitehead automorphisms. So in fact, all I get is inversions. So I just get a finite group. And if I actually want to get the entire GLZ, I also need to add something called twists, which are, I multiply a generator by another generator it commutes with, if I can, and don't do anything to the other generators. Okay, so that's another type of automorphism. It exists. But in general, there's a theorem that says everything in out of A gamma is a product of Whitehead automorphisms, inversions, twists, and that's not quite enough. You also need to include graph automorphisms, which we discussed at the very beginning. So this is proved by Servatius in 1995 using work of Lawrence in 1989. So this is what I've called U0. This subgroup is it's called the twist subgroup, and the whole thing is out of A gamma. And for now, for the rest of this talk, well, until we'll see how far I get, but probably I'll just think about subgroups of U0 of A gamma. So, sorry? Yeah, it's the subgroup generated by Whitehead automorphisms and inversions. Yeah. No, you can apply it to a singleton, or you could do two folds on a singleton, one on the left and one on the right. Yeah. Sometimes it's called the untwisted subgroup, yes. Because it doesn't have twists. Okay, so in fact, in 2014, Hensel and Keelak showed that any finite subgroup of untwisted automorphisms can be realized on some cube complex as cubical isometries. So yeah, isometries that preserve the cube complex structure. However, they weren't, yeah, it's kind of a complicated proof. And we got started on this kind of trying to understand what they did. And eventually we kind of gave up, and we reproved their theorem with what I think is a simpler proof. And it has the advantage that it limits the cube complexes that you use to one of a finite list of cube complexes. This is good because the finite list, of course, depends on gamma, and so they're called gamma complexes. And each gamma complex, well, it's a finite cube complex. It has only finitely many cubical isometries. And so as a corollary, there's only finitely many conjugacy classes of finite subgroups. So that's what we wanted to show. So in order to explain what's going on, I have to tell you what a gamma complex is. Right. Well, if gamma is a complete graph, then a gamma complex is the N torus. That's the only gamma complex. But that doesn't have any untwisted automorphisms either, so we're not really so interested in that one. On the other hand, if gamma is a discrete group, a gamma complex is going to be a connected graph with no separating edges. And all the vertices have to have valence at least. So there's an example. If gamma is the discrete group on 3 points, a discrete graph on 3 points, then there's an example of a gamma complex. So that's right. This has to have fundamental group F3, right? Yeah. So this is not gamma. This is X. This couldn't be gamma. It's not a simplicial graph, right? Yeah. Okay. So fundamental group of X is F3. Right. I want to describe another way, tell you another way of describing these gamma complexes. If I have a graph, I want to put a certain structure on the graph. Any graph, you can find a maximal tree. So here's a maximal tree in this graph. Choose a maximal tree, and I want to label the other edges by the vertices of gamma. So I had 3 other vertices, label them X, Y, and Z. And so this gives me a map from my graph to a standard rose. The rose is actually the Salvetti complex for the discrete group. Okay, so given a graph, the kind that I like, I can put this structure on it and get a map to the rows. But now I want to think of this tree in slightly different terms. I claim that each edge of this tree gives me a partition of the half edges x of the other edges. So x, y, and z each have 2 half edges, and I claim that the tree partitions those half edges. Okay, so what's the first partition? Let's take this edge E1. Yeah. So this edge E1, it has two vertices, that one and that one. At the top vertex, x comes in and y goes out. So I'm going to put x and y inverse in one piece of the partition. At the other edge, x goes out, and y, z inverse, z, all go into the other half of the tree, the rest of the tree. Yeah, maybe I should say this in a different way. The edge divides the tree into 2 pieces. If I remove the edge, I get 2 pieces. Some of the edges end in one of the pieces, the other half edges end in the other half pieces. Is this clear? I feel like I'm garbling this somehow. Anybody want to? Sorry, a half edge. Thank you. So x has 2 half edges. It's got a front half edge and a back half edge. Okay, y has 2 half edges, a front half edge and a back half edge. Z has 2 half edges. I call it z minus and z plus, x minus and x plus, y minus and y plus. Okay, so every edge has 2 half edges. Now if I take an edge of the tree, that cuts the tree into 2 pieces. Like the first edge, there's that piece and there's that piece. Right? Now, some of the half edges land in the top piece. What lands there, x plus, y minus, land in this piece of the tree, and all of the other half edges land in the other piece of the tree. Is that better? Yeah?
So in better way of saying that, you like snip each of these edges that are in the tree, and then each edge of the tree divides that. That becomes like a tree.
Yeah, that's another way to say it. Yeah. So the second edge, E2 down here, cuts the tree into 2 pieces. There's a left half and a right half. And let's see, some of the half edges are attached to the left half and some are attached to the right half. X plus, y minus, and x minus are attached to the left half. Z minus, z plus, y plus are attached to the right half. Is that right? Z minus.
I don't see a z plus here right now.
Yeah, I didn't do this right. Okay. This would be confusing if I don't even have it right. Let me try doing it in real time here. You guys can, so let's do E2, which is what I just did. So x plus x minus and y minus are on one side, and y plus all the rest of them are on the other side. Right? Okay, and P3, yeah. I'm going to get y and z inverse, and everything else should be on the other side. Okay. Okay. So why did I go through all this? Well, these partitions contain all the information you need to reconstruct B. Yeah, so I have these three partitions, this one, and this one. And the green tree is dual to that, those circles. And the other edges are attached according to my partitions. Okay, so this is the takeaway you're supposed to get from this picture. I have this graph, simple looking graph. I'm making it very complicated by describing it in terms of some partitions of the half edges x of x, and y, and z. Okay. Okay. Why did I do that? Why did I bother to do this? Whoops. Right. Yeah, why did I do that? Well, the answer is I'm trying to find these graphs x, and here's a way to describe them. If I give partitions of the half edges, I give you a graph x. Right. And another way to prove that there's only a finite number of such graphs is that there's only a finite number of ways to partition the half edges. So therefore, there's only a finite number of graphs I could construct. Okay. Yeah, you can't just take any partitions. You have to take partitions that work. Yeah. But still, there's only a finite number. Okay. So if you understand that picture, I can explain to you what a gamma complex is. So I can think of what I did back here as blowing up. So that's the Salvetti complex for the free group. And I blew it up by blowing up that central vertex into a maximal tree. Okay? So I want to do a similar thing. Instead of blowing up the rows, blowing up this vertex at the center of a rose, I wanted to blow up the vertex centered at the unique vertex of the Salvetti complex. And I want to blow it up, instead of into a tree, I want to blow it up into a complex, a cube complex, a contractible cube complex. So any blow-up is going to contain a, quote, maximal tree T. Instead of a bunch of edges, it's going to be a bunch of hyperplane carriers. And all of the rest of the hyperplanes are going to be labeled by the vertices of gamma. And if I collapse all of the carriers of the hyperplanes, that's like collapsing the maximal tree. I'm going to recover my Salvetti complex. So let me just do a simple example. That's my graph A, B, and C. I claim that the guy on the left is a blow-up. So to convince you it's a blow-up, I have to find a hyperplane T. I have to and I have to look at the carrier of that hyperplane, which is just the cubes that contain that hyperplane. So that's the green shaded part. and I have to tell you some way to identify. So when I collapse this hyperplane, I obviously get something that looks like that. But part of my blow-up structure also said which one goes where. So let me see, I can make this A, this C, and both of these get mapped to B. So what I've done, in fact, is label all the other hyperplanes. The B hyperplane is complicated. I've labeled all of the other hyperplanes. Sorry, the hyperplanes that are, yeah. Okay, so, right. So again, in this, I'm missing something. Okay. So again, I'm missing a critical slide here. Okay, right. So again, I claim I can describe this picture in terms of some partitions. How do I do that? That's too bad. So this is B, my blow-up. So I claim I can describe B by some partitions. But, here, yeah, no, not there. Lost it, sorry. Okay, I can describe B by partitions, but there's a twist now. The partitions, instead of just having 2 pieces, they'll have 3 pieces. So in this case, I only have 1 partition. It corresponds to the green hyperplane T. And again, it corresponds, it has the front of A and the back of B, of C. And on the other end, it's got the back of A and the front of C. But notice it's got the front and back of B are on the bottom and top of that cylinder there. I'm going to put them all in a separate piece. This is the link of the partition. So P separates, so the partitions are a little more complicated. It's a partition into 3 parts. The first 2 parts separate something from its inverse. And the last part is the link of that thing. Also happens to be the link of B. Okay. So a gamma complex is something you can describe by partitions. That's the takeaway from this. And there's only finitely many partitions, so there's only finitely many gamma complexes. Oh yeah, here it corresponds. I don't know why I couldn't find it. Correspond to partitions, but there's a new feature that, yeah, we've got 3 parts to the partition instead of 4 parts. So again, this set of partitions is a blueprint for constructing a blow-up. I should remark that the same gamma complex can have lots of different blow-up structures. That's just like a graph can have lots of different maximal trees, and even if you have maximal trees, you can label the remaining edges however you want. But nevertheless, if you have a blow-up structure, if you have this description in terms of partitions, you can create X. You can construct X. So, and X turns out to always be a special non-positively curved cube complex with no separating hyperplanes. And again, there's only finitely many ways to partition the vertices of gamma and their inverses. So that means there's only finitely many partitions altogether. There's only finitely many gamma complexes. Right. So if I can prove in 10 minutes that I can find a gamma complex that realizes any finite subgroup, I've proved that there's only finitely many conjugacy classes of finite subgroups. So how do you compute? How do you do this? You need to make a gamma complex. So if gamma group, Color, Kramtsov, and Zimmerman did this already for us. If we can use this as a base case of an induction. So we need something to induct on. So what we're going to do is define a subgraph of gamma to be U0 invariant if whenever you have one of these automorphisms, it takes the special subgroup A delta to A delta. Now what does this mean? Because we're in outer automorphisms, this means phi of A, if you choose a representative for phi, it takes A delta to a conjugate of itself. And the lemma is that if you got a U0 invariant subgraph, then there's a restriction homomorphism that takes you here to here. So if you have a finite subgroup here, you can look at its image over here, and you say that the guy over here, if you have a complex of a delta complex over here, you say it realizes the group if it realizes the restriction. Okay, so what are we going to induct on? We're going to induct on the chain length. We're going to look at chains of U0 invariant subgraphs, and right, there's a lemma that if you got a minimal one, it's always discrete. So if the length of that chain is 0, we're done by Color, Kramtsov, Zimmerman. And in any case, we can always realize the first subgraph in the chain. So now you have to worry about realizing the next one. So what do? We fix a maximal chain. And so we can find, by induction, we can find complexes that realize the G on all of those sub-guys in the chain. And then you study the structure of the graph of invariant chains like this. What do they look like? So you have, look at the last graph and look what you have to do to get to the next graph. The lemma is that if you got two guys, if you look at what's left after you remove delta, if you look at two vertices, they've got the same link intersected with gamma L. So I'm going to draw you a picture of that. Here's gamma's this big graph. Here's my invariant subgraph. And here's the next guy in the chain, next to the last guy in the chain, gamma L. Everything that's in delta but not in gamma L has the same link in gamma L. It might have other stuff connected in other ways, but in gamma L, it's all got the same link. So we'll call that guy phi. And then phi may have a bigger link it may, so it's connected to everything in theta, but it also might be connected to some things in gamma L. We'll call that stuff Xi. And this is what the next stage in the chain looks like. And then there's a lemma that Xi and Phi, and actually the whole blue thing, are all gamma invariant. The only thing in this picture that isn't gamma U0 invariant is possibly theta. So I've got complexes for all of those things by induction, except for theta. So what do I have to do? I have to, yeah. So I've got gamma complexes for all these things, but actually I have to show that, in fact, if I start with a gamma complex of a gamma L complex, then in fact there's a unique choice for phi and a unique choice for xi. So that's probably the hardest part of the proof, but it's true. And the next thing I have to prove is that if I've got complexes for xi, phi, and phi, then I can make a complex for the whole blue part by a variation on the classical realization theorem. So now I've got a complex for gamma L. I've got a complex for the blue thing. I know that these parts are unique. The complexes I get for that and that, I have no choice. So in other words, if I take the complex I build for the blue thing, I can glue it to the complex I have for gamma sub L along these guys, because I have no choice for what to do there. Right. Yeah, so I use these guys that I've made to build the marked complexes for all the pieces. I glue them together along their common intersection, and I get a complex, a cube complex. Yeah. I still have to worry, yeah, the markings all work out. I still have to worry, I'm sorry about going through this so fast, but let me just point out what else you have to do. So I made these cube complexes by gluing a complex here and a complex there along their common intersection. I have to check that what I've made is actually still a one of my blow-ups. And that also requires some work. Yeah, but it's true. So all of this is actually in a paper that came out, well, it hasn't come out yet, but it's was posted on the archive over a year ago. The realizing these finite subgroups. It's been accepted, but it hasn't come out. Right. So it's already been useful. Elia Fioravanti used this theorem to characterize subgroups of A gamma that arise as fixed subgroups of finite order elements in U0 of A gamma. Other possible uses for this theorem that we haven't really explored too much are, like for free groups, they're realized on graphs. Free subgroups of finite subgroups of U of A gamma are realized on these gamma complexes. So maybe you can answer the same sort of questions we could for out of Fn. What's the maximal order of a finite subgroup of U0 of A gamma? And maybe you can classify the finite P groups in U0 of A gamma using the idea that if there is one, it's realized on one of these gamma complexes. So as long as you understand what a gamma complex is, which I realize It may take a little work. You might try to do that. One other thing I wanted to say is another thing, the color realization theorem can be restated as a fixed point theorem. So out of Fn acts on outer space, which is the space of marked metric graphs. And you can just restate this theorem as saying that a finite subgroup has a fixed point in outer space. There's a marked metric graph that realizes it. And it's called Nielsen realization by analogy with Kirchhoff's Nielsen realization theorem. And another, GLNZ acts on symmetric space, and you can use the fact that symmetric space has a cat zero structure to give a different proof of Jordan-Zassenhaus that there's a fixed point. So that gives another description of finite subgroups of GLNZ as those that are realized on flat tori. So Corey and Ruth and I constructed an outer space with an out of A gamma action, which is contractible, has finite stabilizers, and marked gamma complexes like I've described give points in this outer space. So you could reinterpret our result as saying that any finite subgroup of U naught of A gamma fixes a point of O gamma. And from there you can wonder whether the fixed point set is contractible, which has a fancy name. Is it a classifying space for proper actions? And then what we've been doing since we posted this paper is asking, well, what if G is a finite group, but it's not contained in U naught? What if it's, does it still fix a point of the outer space? Is there still a realization theorem for any finite subgroup of U naught? Right. So graph automorphisms seem to be a problem, so let's ignore them and just look at finite subgroups of the rest of out. Right. See if we can find a fixed point for one of those. And the answer is maybe. So I have 1 minute. I want to point out the difficulties. So this outer space that we defined, points are marked metric spaces, but they don't come with a cube complex structure. All you can say about them is that you could divide them into parallelotopes, not cubes, in such a way that if you pretend that all the parallelotopes are cubes, you got a gamma complex. Okay, so the spaces seem floppier. There's lots of ways to divide them into parallelotopes that will work. But the idea of finding a fixed point is similar to what we did in the untwisted case. You want to, there's a similar description of invariant subgraphs and maximal chains of invariant subgraphs, and you want to induct on the length of a maximal chain. That's what we did. In this case, you can't hope that your finite subgroup is going to preserve any of these parallelotope structures. So you have to kind of ignore the parallelotope structure and do everything we did metrically instead of combinatorially. And let me just give a status report. So one thing you get with a cube complex structure is you get hyperplanes. In a general cat zero metric space, you don't have hyperplanes. But we need hyperplanes in order to define the appropriate subcomplexes that we need to construct our complexes that we're building up. So here's the status report. We've defined metric hyperplanes that at least we found enough of them so that we can find the space we need in terms of those metric hyperplanes. There's still some technical problems for constructing points corresponding to disjoint unions of subgraphs realizing gamma, and we're still working on it. We thought this, for a while, my co-authors wouldn't let me submit this paper because they said, oh, we'll just do the whole thing. We won't just restrict ourselves. We'll be another couple paragraphs. So as I said, we submitted the paper on, put the paper on the archive over a year ago, and we're still working on this. But yeah, anyway.